Hello, and welcome back to Learning with Lee. In today's episode, we are going to take a look at iterators, why we use iterators, why iterators were created, and the theory behind iterators. To begin with, let's talk about what an iterator is. An iterator is an abstraction of a pointer, and that might sound a bit more complicated than really what it is. If I have some iterator here, and we'll just call this IT, and then I have some pointer over here, P, and I'll just use a little squiggly line over here to signify that it happens to be an abstraction of P. Basically, the important thing about P is that if I have something like an array, I have to know how to basically access a certain element in there so I can point to an element. I might end up using a subscript off of this first one, so I could do something such as P sub 2, which would be the same as having this point to this exactly. Or I could have P pointing to 0 and then just add 2 to it. However, that implies certain things about the memory, the fact that this is one contiguous block of memory, as well as then how I end up modifying it, stuff such as the fact that I can actually read and write to this array. Happens to be specific to this type of pointer that I'm using, and to this data structure of an array. Alternatively, if I have some, let me just do a little squiggly line over here. We can call this guy P also. And it's pointing into a linked list. It's going to have a very different way of going from this element to the next element. It's going to have a different way in case I try to go from 1 over to n minus 3. And then all of that is going to end up having to be specific to my linked list. So then we run into problems of, let's say that I currently have over here this little P1, and I want to then go to P2, and all of my old code happens to be using this P1 mechanism, happens to be using arrays, and I want to change some of it over to lists. If this is a large-scale industrial application, we could be looking at changing thousands upon thousands of lines of code, because of the fact that you might end up using this data structure through a massive chunk of your program. And this can end up leading to a bunch of bugs if you are tightly coupled. And what I mean by tightly coupled is that there's a term in computer science known as coupling. And it is used to represent how closely related your code is and how dependent your code is on some other piece of code. So, in case you end up using some third-party library a bunch throughout your code, you're going to be fairly tightly coupled to that library. In case you end up then wanting to change libraries, say in case it were some UI that gave you some custom look and feel for your program, and then you want to change to a different one, the more things you end up having to change in order to make that change, the more coupled you are. And the problem with that is that the more coupled you are to something, it increases the amount of development time you have, it increases the odds you end up having bugs, it makes it harder to make changes, such as in case you find a bug in one particular subroutine or function. What you might end up having to do is the changes that you make to that could inadvertently cause bugs in other portions of your program if it is tightly coupled. Ideally, you want fairly loosely coupled code so as that you can change one portion of your code or you can change third-party libraries without having to change the rest of your code by extension. And the point of abstraction is to reduce that coupling, to make it so as that you have to do fewer changes when you convert from one thing to another. And in languages such as C# or Java to a certain extent, you can do certain things with collections, and in particular in C#, there happens to be, if I just type it out over here, what is known as an IEnumerable, and that basically allows you to use things such as a list, whether it is in this form, whether it happens to be in this form over here. It allows you to end up using, even if you want to, a tree, or a priority queue, or a heap, or any number of other things, and be able to go over all the different things in there. And it's a very similar thing to an iterator, just at a bit of a higher level of abstraction even than an iterator. But it's so as that you can basically switch in and out one of these data structures for any of these other data structures without having to care what they are, and allowing for your algorithms and your logic and your functions to end up doing the exact same things without having to make any significant changes to those algorithms and to that logic. So that's the major goal of decoupling and the major goal of iterators in general. So what does an iterator need to do? It needs to be able to, as we've already discussed, go, okay, I need to know how to go from element 1 to element 2 and to element 3. So that means that we need to have some form of a plus plus operator. In the event that we're allowed to go backwards through our list, and there are certain situations where we wouldn't be able to, because in case you remember when we were initially going over linked lists, I discussed how we might have a singly linked list, where basically it doesn't have this backwards pointer. In case I hop over here and we take a look at our links, you'll remember that in here we end up having things such as our previous and our next. Well, in case it didn't have previous, and you can create these in a valid manner that way, it would be a singly linked list. And as a result, it would really only make sense to iterate over it in this single direction. In case you had to go from, say, 1 to 0, you'd have to end up going over literally every single element in here to wind up back here. You could do a bit of shortcutting to be like, okay, I'm going earlier in the list, then I can just basically skip back to the starting point, since I would obviously have that in my parent linked list, and then head back through it. All that information and having that logic in there is very specific to a linked list. It is not general for any type of data structure that you could use, even though the fact of the matter is that you want to end up using iterators across those. So while we need minus minus for certain things, it is an optional parameter, and it's specific to certain versions of it. So I'm going to put this question mark here just to signify that not every single iterator is going to allow you to decrement it. Then, one of the other things you need to be able to do in general is typically you need to be able to access whatever you're pointing to, whether it happens to be an element in an array, whether it's a link, and occasionally you might want to even hide the fact that it's a linked list. So rather than getting the link back from, in this case here, the operator happens to be this operator here, alternatively we can also do the dereference operator of using this, because as I said, this is effectively a pointer. So it would be the same as in case I had some little int pointer p, and we'll just call this pi. And that happens to be basically what it is, and you can do the same stuff such as these two operators on a traditional int pointer. So we do need element access. That isn't actually, though, necessarily something that we're actually going to care about, because there is one situation that is a bit awkward, and we'll get into it more in a little bit. And that's the situation that I'm going to describe down here, of supposing you can only read or write, but not both. For a linked list and for an array, and to a lesser extent for things such as, in this case here, it might be a binary search tree, you want to be able to write to elements in addition to reading them. As a result, you're going to have to be able to go, okay, I need to access certain things within there. I'm also going to therefore need the ability to dereference and then do the equals operation. So those are things that you have to consider the possible need for. But in some situations, the assignment, so I'm just going to move equals down here, is itself optional. It doesn't necessarily need to actually occur. Then you need to be able to do things such as in case, and this is once again somewhat of an optional thing, be able to do something like plus equals. So if I wanted to go from wherever I'm at in here, and I then want to basically jump down to, say, down here, I want to be able to add in some number to that. If I'm doing that for something such as a linked list, it can still be done, it's just a bit harder to do. There is a bit of a larger issue when we end up dealing with things such as a binary search tree, or in case we end up dealing with things such as files, or any other stream of information in which we might not have the ability to jump ahead that far. Or it needs to, behind the scenes, still do it in basically an element by element manner, like in this linked list, but it can effectively do that. It just is effectively doing plus plus a certain number of times. The final operator that iterators need to worry about happens to be the comparison operator. I might want to compare two of these different elements in here, or two of these different elements in here, but whether or not I'm comparing the actual pointer that is abstracted by the iterator, whether I'm comparing, say, in this case here, this is some node, and it has some item within that node, am I just comparing those nodes or am I comparing those items? So that happens to be implementation specific, and as a result, we need this comparison operator to be able to abstract that. And similar to plus equals and similar to equals, that isn't necessarily something that we need to do. So for now, I'm just going to mark it as a question mark. Then, the next important thing to really understand is that there's a few different types of iterators. The most narrow types of iterators are the reading and writing iterators. So these are ones where you can either only output or you can only input. So let's say that I happen to be here, so I'm just going to call this me. I might be able to read in from some buffer in memory, and the most common scenario for this is when you're dealing with sockets, when you happen to be dealing with the internet, and when you're dealing with things that go across multiple computers. Traditionally, you might have used, before the era of the internet and before modern networking, a single computer with shared memory similar to an array to basically pass information back and forth between multiple processes running on the same machine. However, then you might want to convert some of that so that you end up using the internet. So I've got my machine and I've got some other machine over here. We can just call this one here C for the consumer. And it might be able to then read from one and write to the other. And this in general is how sockets work in a very high level overview, is that you end up having some buffer of memory that your consumer can write to and you can read from, and then there's some buffer of memory that you can write to that then gets sent to your consumer, and technically these buffers are duplicated on each machine, so I could do a little thing like this, so that effectively you have your buffer here that you're reading from, and then it basically gets transported across the internet at this little layer here, and I'll just sort of link these up and call this I for the internet. And it ends up getting put into some buffer where C can read from it. However, it makes no sense for C to write back into this one here. It only makes sense for them to read from that buffer. Because if they write to that buffer, all that they're modifying is data that only they can use. That buffer never gets sent back across the internet to over here. You can end up doing some work in order to effectively do that, but at the same time, really you still end up going through this process. You just then are effectively creating another buffer off to the side that gets duplicated and ends up storing the same information. But realistically, it's a matter of you're going to have something that you read from and something you write to pass across to C. So it makes no sense for this one here for you to be able to read from it, since you're the one writing to it and you're the only one writing to it. As well as also, it's specifically designed to be sent across. So that happens to be one particular use case in which you're only going to want to read or to write. Another situation is that, and this is a bit more of something we haven't gone into, and it's more of a sysadmin style thing. And by sysadmin, I mean system administrator. Just very common abbreviation of that for those who have never heard that term before. And that's that occasionally some files you might not have the permission to write to. You might have the permission to read them, but either due to security clearance or because of you're not in the correct group or something else like that, you're only allowed to view those files. You're not allowed to modify them. As a result, it doesn't make sense for you to then be able to write back to that file that you're reading. Or in some cases even, you might have the ability to output to a file, but you can't read that file. And we'll get into a whole bunch of different security-related things, decent ways in the future when we get into different security models and patterns and paradigms. But that is the basic level of you have these input ones and you have these output ones. Then, off of those, you have what are known as basically unidirectional. And those are the example I gave here, where we can go around in this loop, but we can only go one way. We only have access to this, but now, in addition to being able to read and write, because basically this one, it's not actually derived off of these, though it could have been, but in this case here, it isn't, but it adds in the ability to increment, doesn't give us the ability to decrement. It doesn't give us the ability to do plus equals. It allows us to compare, allows us to do assigning, allows us to do reading, so that happens to be the next layer. Then, after that, we have the bidirectional, so something like this, in which we can now also do minus minus. And then finally, there is this layer here. And this happens to be what is known as a random access iterator, because it has the ability to go, I'm going to, by a single operation, just go from p pointing at 2 to p pointing at n-3 just by adding a single value to p. It allows me to basically go, this is a contiguous chunk of memory, whereas in this case here, these, if I basically started laying them out, they might be at a whole bunch of different spots in memory, with a whole bunch of different little random junk in between them, and who knows how much stuff there happens to be in there. And they're going to exist at different spots on the heap. So I can't just go, okay, I have some pointer here, I'm going to add some value to it because I might wind up all of a sudden down in here. And quite frankly, it might also end up with this guy being our first one pointing to this one here, which then points to this one here. And that could all lead to a fairly large number of problems if we were to try to do this plus equals operator for that case. It could be done, but effectively is just calling this a certain number of times, however many times you specify in this. So if I did plus 15, it would give 15 increments. Because I would have to go, okay, starting at 1, go to 2, go to 3, and so on and so forth until I hit that 15th one. So that happens to be the final and most powerful case of iterator, which is the random access iterator. In the next episode, we're going to get into how to begin to convert our links and our linked lists from earlier in this series so that we can actually get iterators for them and use iterators for them. Thank you very much for watching. Have a wonderful day,